Ladies and gentlemen, let's continue with our course in heat transfer. We make use of the textbook of Cengel and Ghajar, 5th edition, and we are busy with chapter 6. We had a previous lecture on it, and this will be our second lecture on this chapter. Now, the lecture was a little bit boring, the previous one, because we have revised work that you've already done in fluid mechanics. And that was specifically paragraph 6.1, the physical mechanism of convection. 6.2, the classifications of fluid flows, where we've looked again at viscous flow versus inviscid flow, internal versus external, compressible against incompressible, etc. And then also the velocity boundary layer, how the velocities vary in the boundary layer. And today we are going to start with now something that is new, but also you will see very similar to what you have found in fluid mechanics. And that is the thermal boundary layer. Now, just before we get to the thermal boundary layer, let's look at the velocity boundary layer. So VBL is just a velocity boundary layer, and we consider the case of having a free stream velocity V infinite, and we have what is called a no-slip boundary condition. So here on the wall, the velocity would be equal to 0, and then the velocity will increase until it's the same as that of the free stream boundary, as the free stream velocity. However, let's suppose that free stream velocity is 10 meters per second. Then the boundary layer thickness will be at 99.9% or 99% of that velocity. So let's suppose that velocity is then equal to 9.9 meters per second. Then that distance will be known as the boundary layer thickness. So that is for the velocity boundary layer. And in the beginning, it sometimes helps to distinguish the two boundary layers, the velocity boundary layer and the thermal boundary layer, with two colors. So I normally like to use blue for the velocity boundary layer, and now we're going to introduce the thermal boundary layer. Principle is very similar if we've got a free stream, but now at a certain temperature, T infinite, and uniform to a flat plate or a surface. So that again is a flat plate like that. What will happen now? Let's suppose that free stream temperature is 100. Well, I've already made an error here. This is not supposed to be arrows because temperature is not a vector. Okay, so let's draw that as lines of 100 millimeters. So let's suppose that temperature is 100 degrees Celsius or 100 Kelvin or 100 degree Fahrenheit, it doesn't matter. So, and this surface is being kept at a temperature of 20 degrees Celsius. So what will happen with the temperature boundary layer is that this distance will be 20. Okay, that would be 20. Because that is equal to the surface temperature. Just like with the velocity, a no-slip boundary condition, this can't be 0 degrees because the plate is not at 0, it is at 20. It's at a lower temperature, and then it is going to increase up to that value of 100. And we are going to have a temperature gradient like that. Okay, so that is equal to T infinite, which is 100 millimeters in length. And that shows the boundary layer. And that temperature gradient gives us minus dt dy, I think divided by k or something like that. That is the equation that we've derived the previous time. Something like that, where y is equal to 0. Okay. But the important thing is that the thermal boundary layer, which is now delta T, the T indicates the thermal, is equal to 0.99 times the temperature difference, T infinite minus T surface. So for this case, let's do the calculation. T infinite is 100, the surface temperature is 20, and that is equal to 79.2 degrees Celsius. Thus, if we go up with the temperatures, and that is maybe equal to 90, and there is 80, so up to 79.2, then that distance will be the thermal boundary layer thickness. I hope you can see the similarity between the two. Of course, the special case where the plate is at 0 degrees Celsius, that special case, then the thermal boundary layer thickness will be at a temperature of 99 degrees Celsius from the wall. You follow? Let's not. Okay. So this is the case of 20 degrees and 100 degrees. So the boundary layer, thermal boundary layer thickness is 99% of the difference between the two, 100 minus 20. Okay. Now let's look at the special case where the surface temperature is 0. Then the thermal boundary layer thickness again is 0.99 times multiplied by the temperature difference, which is 0.99. The free stream temperature is 100 minus surface temperature 0, so that would be at 99. At 99 degrees Celsius. That is where the thermal boundary layer thickness will be. You follow? Any other questions? Okay. Let's introduce the Prandtl number. Prandtl number? The Prandtl number, per definition, is the molecular diffusion of momentum. Okay. Divided by the molecular diffusion of heat. The ratio of the molecular diffusion of momentum divided by the molecular diffusion of momentum. And by definition, it is going to be equal to the viscosity, Cp, divided by the thermal conductivity, K. And you can also write it as the thermal diffusivity, the kinematic viscosity divided by the thermal diffusivity. Those properties are always given in your textbook. So in all the problems, it's normally stated. You're working with oil, water, a gas, or whatever. At the back of your textbook, before your first test, you need to know exactly in which table you're going to get that, because you're going to use it a lot in the tests and exams, and you do not want to waste any time. Now, let me explain to you the difference between the velocity boundary layer and the thermal boundary layer taking into consideration the Prandtl number. And we are going to consider 3 cases. The first case will be the Prandtl number equal to 1, then a Prandtl number smaller than 1 and a Prandtl number larger than 1. Let's just look at fluid mechanics on its own. You've done it last year and we've revised it with a previous lecture. There will be a thermal boundary layer. Let's make it in blue. There's your thermal boundary layer. And that would be the boundary layer thickness. And here we will have the y-axis and there's the x-axis. So that is the case where we only have fluid flow around or over a flat plate or a body, typically. But now we're also going to introduce some heat transfer. Now for all these 3 cases, let's draw the boundary layer there. Typically maybe a velocity of 100 meters per second. Okay, so that would be the velocity boundary layer. Prandtl number, as I've said, is the ratio of the molecular diffusion of momentum. So let's write it like this: momentum divided by heat. Momentum divided by heat. Momentum, the diffusion of momentum divided by the diffusion of heat. Now let's give momentum an arbitrary value. Let's suppose 10. Okay. If it has a value of 10, to get the Prandtl number to 1, then that must also be 10. The rate of diffusion of the 2 are the same. So therefore, the 2 boundary layer thicknesses will lie on top of each other. That is a special case of Prandtl number equal to 1. The Prandtl number is smaller than 1, and we have chosen the momentum diffusion as 10, then typically that would be 20, which gives us a Prandtl number of 0.5. So for that case, the thermal boundary layer would be smaller than 1. And for this case of the momentum, again, we've chosen the momentum diffusion as an arbitrary value of 10. Then, for the Prandtl number to be larger than 1, then this value must be smaller. Let's suppose 5. So therefore, that ratio is 0.5. And this thermal boundary layer thickness will then be there. the momentum diffuses faster than the heat and the other way around. So that is a very simple way of understanding why the two boundary layers behave as it does. Now typically Prandtl numbers smaller than 1 would be liquid metals, something like mercury or sodium, and those are typically used in nuclear reactors where you want to get rid of heat very quickly. Prandtl number equal to 1 is actually most of the gases. Air, depending on the pressure and temperature, has a Prandtl number of approximately 1. And then Prandtl numbers larger than 1 are typically liquids, such as water. Water has a Prandtl number of about 7 to 10, depending on the temperatures and the pressures. And glycols has Prandtl numbers of 30 and 50. Glycols are typically used in car radiators and also in air conditioning and refrigeration systems so that the fluid doesn't freeze. There's a question there at the back. I beg your pardon? One of my Prandtl numbers have to be 2, yes. Sorry, this one. I beg your pardon? I'm sorry, I still cannot hear the question very well.
So I'm then asking if the middle column is still correct.
If the what?
I'm then asking if the middle column is still correct.
Is the middle column the graphs? Is it correct?
I'm asking are they still correct according to you?
Sorry, I cannot hear you.
I'm asking if now that you've adjusted to 2,
Yes.
are your graphs still correct?
Is what correct? The graphs.
still
Yes,
correct.
the graphs are correct.
Okay.
Because look at so yes, I've made a mistake there. At the end of this semester, you will know there's quite a difference in terms of what I mean, write and say sometimes. But I'm quite sure you will pick it up quickly. So in terms of a relative value of the momentum diffusion, if the heat diffusion is smaller, then the Prandtl number would be larger than 1. So the heat diffusion is smaller than that of the momentum diffusion. And then, of course, in this case, it's the other way around. The thermal boundary layer is now thicker, while with a Prandtl number of 1, they lie on top of each other. I hope that answered the question. Okay. In terms of fluids, just to give you an indication of Prandtl numbers, at the end of this semester, you will have a better feeling for it. So for liquid metals, typically the Prandtl numbers on the order of 0.03. For gases, typically for air, the Prandtl numbers vary in order of magnitude of about 1. We are always interested in air and water. Prandtl number of water is about approximately 10. Then oil would be values of 50 and higher. And glycerine will have values of 2,000 up to 100,000. Oil can also have Prandtl numbers up to 100,000. Just to give you an indication. Okay, now the Prandtl number was named after Ludwig Prandtl. He's a very famous scientist, engineer, about 1875, about 200 years ago. And he was a pioneer in the development of rigorous systematic mathematical analysis, which he used for the underlying the science of aerodynamics. So all of you interested in aerodynamics, you're going to learn much more from his work. And it was because of his outlook on fluid mechanics that many of the very simple equations that were derived to determine lift and drag many of those equations was developed by him. Now he studied in Germany and he worked there. He became a professor in fluid mechanics in 1901 at the Technical University Hannover, and in 1904 he delivered a groundbreaking paper which is fluid flow in very little friction. You can go and read about him, is very interesting, but one of the interesting things that I've picked up is that apparently his life was marked by overtones of naivety. At the age of 34, he decided it was time to marry, so he went to his old professor, which was August Foppel, to ask his daughter's hand in marriage. And that night, when the professor came home to discuss it with his wife, he realizes he actually has 3 daughters. And Professor Prandtl didn't say which one, but between them, they decided on the oldest one, and apparently that was fine, and the marriage was long and a happy one. And he worked at Göttingen. He worked at Göttingen until he died in 1953, and he is rather considered as the father of fluid mechanics and also of aerodynamics. So a very interesting guy. And then there's apparently a crater with the name of Prandtl on the far side of the moon, which has been named to his honor. Okay, paragraph 6.5, I'm going to say a little bit about, because you've done that in fluid mechanics, and you are going to look at it again in MKM, the derivation of the most simple equations of continuity, momentum, and energy. Question?
Sorry, Professor. So what's the significance of the thermal boundary layer? What does it mean?
The significance of the Prandtl number, of the boundary layer thickness.
Yes. What does it mean if we're inside versus outside the boundary
Yeah,
layer?
it is very important. I'm going to come back to it over and over and over again in heat transfer. And the significance about it is that if we are interested in the heat transfer coefficient over a body of a certain length, then it means that this thermal boundary layer will be a direct indication of the heat transfer. So if the thermal boundary layer is very small, like typically here it is equal to 0, then the heat transfer coefficient is infinite. And then it is going to decrease until it is what we call fully developed. And that is very important to know what part is developing flow and which part is fully developed flow. In terms of getting the heat transfer coefficients so that you can do your design, normally you need the heat transfer coefficients to determine how much area you require to transfer a certain amount of heat. So this shows us if the boundary layer is developing, then the heat transfer coefficients are much higher than when it is fully developed. If it's fully developed, then it stays constant. So many of the equations which are available in industry would typically have these values, which are the fully developed one, which are the simpler ones. And you will ask why? Well, the reason is it's more conservative to use a smaller one than maybe the average one. But again, if you want to be competitive in designs, then it is very advantageous to know exactly what happens, because then over a certain length of your heat exchanger, you can better go and determine the average value which would be higher than the conservative value of fully developed flow, which means that most probably your area can have less area, less material, less cost. Okay. It is also important to understand that this boundary layer can actually be disturbed because by putting in disturbances, you can keep on changing this boundary layer to be very high. You can change the boundary layer to start growing again every time. And when you do that, the heat transfer coefficients will increase significantly, and that is part of heat transfer which is known as enhanced heat transfer. Okay. Any more questions? Right. Laminar and turbulent flows. You've already done that in fluid mechanics, so very simple. If that is the velocity u, and you have the most sensitive type of instrument that you can use to measure in a fluid stream. And let's suppose the flow stream is a very, very low velocity, then as a function of time, you'll be able to measure a constant value. So the value is equal to a constant value, and it's not a function of time. So if the velocity that you measure here is 1 meters per second, 1 meters, 1 meters, 1 meter, there will be no fluctuations in your reading. However, if you increase the velocity up to a certain value, then something interesting is happening, and that is turbulent flow. You get these fluctuations. And the higher the fluctuations, the more turbulence would be in the flow. However, what is at least helpful is the fact that the average value stays constant. So the measurements will all vary as a function of time, but if you take the average over 2 seconds, 3 seconds, 5 seconds, you'll get the same value. So that is turbulent flow. And for turbulent flow, the velocity is then actually equal to this average value plus a fluctuation component, how much it fluctuates around the average. You've already done that in fluid mechanics, I believe, and one of the simplest way of determining laminar and turbulent flow is with a Reynolds number. The Reynolds number, which is the ratio of the inertia forces divided by the viscous forces. F is forces. I can write it out for you. And that ratio is equal to the viscosity multiplied by the velocity multiplied by a characteristic length. And that characteristic length is not the characteristic length that you calculate in paragraph 4.1 for the lump system. Okay? Divided by the kinematic viscosity, or you can use the dynamic viscosity, which is the viscosity divided by the density, and then you can write the Reynolds number as the velocity multiplied by the characteristic length divided by the kinematic viscosity. I hope you all remember that. Okay. Now, one of the very simple things that are being used with the Reynolds number is to determine if the flow is laminar or turbulent. So if you have a flow condition and the the Reynolds number is 10, then most probably it would be laminar flow. If it is 10 million, then most probably the flow will be turbulent. Okay? So the question is, when does transition occur? Can you remember from fluid mechanics? Anybody? 2,300. Okay? Do you all agree? Okay. You are all incorrect. 5 times 10 to the 5, he says. Okay, why? Okay, the answer is you are not actually incorrect always. There are some cases where it is like that, and that is the cases of flow through a pipe or a tube only. Okay, so only for the case of a tube, transition will occur for Reynolds numbers of about 2,100 to 2,300. Okay. If it's for a flat plate, then it is about 500,000 to 1 million. If it's for your polo, it would be a certain value, and if it's for your conquest, it would be another value. So it depends on the geometry. It always depends on the geometry. Paragraph 6.6, heat and mass transfer in turbulent flow. You're not going to do it. You do that in MKM, as well as the derivation of the differential equations. You actually already did that in MTV 310, so we are skipping that, but please just look at that. And then paragraph 6.8 is important for us because there is something new there. And paragraph 6.8 is the solutions of convective equations. Because there's something that can be derived there that is very useful to us in heat transfer. And again, it is considering the same problem that we've considered previously, and that is of a flat plate. Now, why a flat plate all the time, over and over and over again? Because it's the simplest geometry available. The equations that we are going to write down there now are, as you've learned, quite complex. You end up with the Navier-Stokes equations, the continuity equation, and the energy equation in 3 different directions. And if anybody of you would like the Fields Medal, the Fields Medal is like the Nobel Prize in the Nobel Prize. So there's no Nobel Prize in mathematics. There's the Fields Medal. So if any of you want the Fields Medal, you need to go and solve the analytical solution of the 3 equations of continuity, momentum, and equation. The Navier-Stokes equations. If you can come up with an analytical solution for it, then most probably you will win the Nobel Prize. Not the Nobel Prize, the Fields Medal. Right. Now, if we consider this problem, and I'm not going to look at all the terms one by one, I just want to give you a little bit of background. Then we're going to look at the continuity equation, and the continuity equation can then be written as du dx partial plus dv dy partial plus dv dz partial is equal to 0. And of course, there will already be an assumption here in the sense that it is for constant density, so it's incompressible flow. So there are many assumptions that are being made in these equations. The continuity one, the next one is the momentum one, is u du dx plus v du dy is equal to v partial d2u dy squared, the momentum equation, and the third one is the energy equation. And the energy equation is u partial dt dx plus v partial dt dy is equal to alpha partial d2 t dy squared. That's the energy equation. Now, why was it written like this? Because they've tried to make the geometry very, very simple. They've made lots of assumptions like incompressible flow, steady flow, etc., etc. And these three equations are almost the most simple that you can get for fluid mechanics and heat transfer. And then enters a guy with the name of Blasius, and Blasius looks at these equations and he says, okay, what am I going to do to solve this? And he realizes there are, of course, three boundary conditions needed. The first boundary condition, of course, no slip velocity, and far away the velocity is equal to u infinite. And then with the thermal boundary layer, Ts here on the surface, and T infinite, and he uses all those boundary conditions. And then in 1908, he already came up with a sort of an analytical solution for this problem by defining a so-called similarity variable as y multiplied by v divided by the kinematic viscosity x. And by doing it, he could actually take these two partial differential equations, two PDEs, partial differential equations, and he then generates one ordinary differential equation from it. And that is being done by using so-called stream functions, which you've done in fluid mechanics. Those are the stream functions for the u velocity and the v velocity. Of course, he made the assumption there's no flow in the z direction. And the result of that was then this third order differential equation, which is 2 times d3f d eta third plus f d2f d eta square is equal to 0. So a third order differential equation, excuse me, not a partial differential equation. Okay, so that's the solution for those two. But then he also realizes I can define a function f as a function of eta, which is equal to the stream function divided by the velocity and the kinematic viscosity of x divided by v, something like that. And again, he uses the boundary conditions, and then he had an equation that he can solve, but for that he needed a power series expansion. And what he did is he looked at eta, f and df d eta, which is equal to u divided by v, and then also to the second derivative, d2f d eta square, like that. And as I said, you can solve it with a power series by hand, or already about in the 1970s and the 1980s, they could start solving it numerically using the Runge-Kutta method. I don't know if you can remember the Runge-Kutta. Now, the solution is lots of numbers. And many people will look at the numbers and they would not really see what Blasius saw. Okay. And the numbers are typically from eta equal to 0, then f is 0. That value is then also equal to 0, and that value is 0.332. Okay, so what? Okay. Let's look at another value. Of course, you can solve it for 0.1, 0.2, etc. For 0.5, I just want to put in some values here to show you. 0.042 and 0.166 and 0.331. And then somewhere here, there's a value of 4.91. And then this value is equal to 0.9. Sorry, 0.99. And then for a value of 6, it's 4.280 and 0.999 and 0.002. And if you look at this carefully and actually know what you're trying to do with your mathematics, you will realize that this is actually the magic number that he was looking for. 99% of the free stream velocity. If we go back to the velocity boundary layer, 99%, okay? What happens at 99%? Well, the value of eta is 4.91. And what he then did is he related it to saying that eta is equal to y multiplied by the velocity v, that would be in the y direction, kinematic viscosity in x, sorry, not in the y direction, in the x direction. And then he realized that this value of 4.91 is this value here, is equal to then the boundary layer thickness, y is in the y direction, so that is the boundary layer thickness, multiplied by the velocity, kinematic viscosity divided by x. Therefore, you can write the velocity boundary layer as equal to 4 times 9.1 divided by the square root of the velocity divided by the kinematic viscosity in x. So this is where this special number of 4.91 comes from the solution. And then you can rewrite this in terms of Reynolds number, and the result is that you can actually write this equation as 4.91 divided by the Reynolds number of the fluid at point x. It's a local value, and I will show an example a little bit later on that. But remember, this is for laminar flow only, so all the assumptions has been made, incompressible, laminar, etc., etc. It's not for turbulent flow. And that was the solution then of the boundary layer thickness. You can use this to go and calculate the skin friction coefficient for a flat plate. CF is equal to 0.664 Reynolds X to the power of a half, and the shear stress as 0.332 multiplied by the viscosity, the kinematic, the density, viscosity, velocity divided by x. And if you want to go and make it neat, you can write it as 0.332 multiplied by the density v squared divided by the square root of the Reynolds number. Now that equation is very handy because it's one of the most simplest geometries that can be considered. So if you, for example, have a truck with a container on, and that container is 10 meters in length, then it would be a good assumption to say, well, let's consider that area as a flat plate. And you can use this to estimate approximately the thermal boundary layer thickness, and from the thermal boundary layer thickness you can get the skin frictions and the shear stresses on the material. So in the early days of aerodynamics, that is how airplanes was designed. The fuselage of an airplane also was considered as a flat plate. The curvature is very small in comparison with the total length, and that was actually not too bad assumption. Now, what was done for the thermal boundary layer equations can also be done for the energy equations. And then for the energy equations can then be solved that the local Nusselt number, which is equal to the heat transfer coefficient multiplied by x divided by k, is equal to 0.332 multiplied by Prandtl to the third multiplied by Reynolds x to the half. And guess what? This value of 0.332 is that value there. You see it? So if you really know what you're looking for, then you can get those very special values. But be careful of just solving equations. It's always very dangerous doing that. Together with this, we can use this relationship of Prandtl number in terms of the molecular diffusion of momentum divided by the molecular diffusion of heat to determine that this ratio of the two thermal boundary layers, not the two thermal boundary layers, the velocity boundary layer and the thermal boundary layer, is equal to Prandtl to the third. So if you've determined the velocity boundary layer and you've got the fluid characteristics, you can determine the thermal boundary layer thickness very easy. And the result of that is then also that in general your thermal boundary layer thickness can be written as 4.91 divided by Prandtl to the third square root of the local Reynolds number. And why it is the local Reynolds number, that I'm going to do with you in the next lecture, and it will become more clear then. Any questions, ladies and gentlemen? Not? Thank you very much. Then I'll see you tomorrow.